Hello students, welcome to my second lecture on thermodynamics. In today's lecture, we'll study about measurement of delta U and delta H, calorimetry, and enthalpy change delta RH of a reaction, that is reaction enthalpy. Finally, we will study about enthalpies of different types of reactions before answering multiple choice questions. In the previous lecture, you studied about thermodynamics terms, types of systems, state of systems, internal energy as a state function, applications, work, and enthalpy. Please go through my first lecture. The link of the first lecture is given in the description part of this lecture. I welcome you once again. Measurement of delta U and delta H, that is calorimetry. We can measure energy changes associated with a chemical or a physical process by an experimental technique called calorimetry. Measurements are made under two different conditions. One, at constant volume QV, Q subscript V, and at constant pressure Q subscript P. Delta U measurements, that is, delta U is change in internal energy. For chemical reactions, heat absorbed at constant volume is delta U and it is measured using a bomb calorimeter shown in the figure. This calorimeter is made of austenitic steel which provides considerable resistance to corrosion and enables it to withstand high pressure. In the calorimeter, use of strong cylindrical bomb, which is the central part of this bond calorimeter, and in which combustion occurs. So combustion occurs in the central part, that is, it is a stainless steel bomb shown in the figure. The bomb has two valves. One valve for allowing oxygen inside the bomb and the other releases the exhaust gases. A crucible in which a weighted quantity of fuel sample is burned is arranged between the two electrodes. Here there are two electrodes and in between the two electrodes there is a crucible in which the quantity of fuel is burnt. The calorimeter is fitted with a water jacket. This is a water jacket shown in the figure with which surrounds the bomb. To reduce the losses due to radiation, calorimeter is further provided with a jacket of water and air. A stirrer for keeping the temperature of water uniform and a thermometer which measures the temperature for an accuracy of 001 degrees Celsius is fitted through the lid of the calorimeter as shown in the figure. All these parts are shown in the figure. The heat released by the fuel on combustion is absorbed by the surrounding water and the calorimeter. There is no change in the volume of the vessel. Therefore, delta V is equal to 0 and no work is done as the reaction is carried out at constant volume in the bomb calorimeter. Temperature change of calorimeter produced by the completed reaction is converted into heat at constant volume by using the known heat capacity of calorimeter. We can calculate the change in internal energy which is given by the relations delta U is equal to capital C into delta T into M, capital M by small m. In this equation, small m is the mass of the substance, that is the substance inside the crucible, and delta T is the change or increase or rise in temperature. Capital M is the molar mass of the substance, and capital C is the heat capacity of the calorimeter. Using the known values of heat capacity and m of the molar mass of the substance, we can measure delta T, which in turn gives the value of change in internal energy. Measurement of change in enthalpy. Measurement of heat change at constant pressure, generally under atmospheric pressure, can be done using a calorimeter as shown in the figure above on the screen. We know that at constant pressure, change in enthalpy equals Qp, that is the quantity of heat at constant pressure, and therefore heat absorbed or evolved is equal to is Qp at constant pressure, is also called heat of reaction or enthalpy reaction delta RH. In exothermic reaction, heat is evolved and the system loses heat to the surroundings. Therefore, Qp will be negative and delta RH will also be negative. Whereas in exothermic reaction or endothermic reaction, heat is absorbed and Qp is positive and delta RH will be positive. Let us take one numerical example. Question. 1 gram of graphite is burnt in a bomb calorimeter in excess of oxygen at 298 Kelvin and 1 atmosphere pressure according to the equation C graphite plus oxygen in gaseous form combine to form carbon dioxide, which is a gas. During the reaction, temperature rises from 298 to 299 Kelvin. If the heat capacity of the bomb calorimeter is 20.7 kilojoules per Kelvin, what is the enthalpy change of the above reaction at 298 Kelvin and 1 atmosphere? Please read the question again and interpret all the given terms and note down. Answer. Suppose Q is the quantity of heat from the reaction mixture and Cv is the heat capacity of calorimeter, then the quantity of heat absorbed by the calorimeter is given by the relation Q is equal to Cv into delta T, where Cv is the capacity at capacity of the calorimeter and delta T is the change in temperature. Quantity of heat from the reaction will be the same magnitude but opposite sign because heat is lost by the system, that is reaction mixture, and is equal to the heat gained by the calorimeter. Therefore, using the equation Q is equal to minus Cv into delta T, which is given, the value is given as 20.7 kilojoules per Kelvin, that is equal to, the negative sign indicates the exothermic reaction. Thus, the delta U, the change in internal energy for the combustion of 1 gram of graphite is we have calculated as minus 20.7 kilojoules per Kelvin. Therefore, for combustion of 1 mole of graphite, it will be 12 grams per mole, that is capital M, into minus of 20.7 kilojoules divided by 1 gram. Therefore, that is equal to minus 2.48 into 10 to the power of 2 kilojoules per mole. Since the value of delta Ng equals 0 using the equation delta H is equal to delta U plus delta Ng into RT, we can calculate the value of delta H equals delta U as minus 2.48 into 10 to the power of 2 kilojoules per mole. Enthalpy change, that is delta RH of a reaction. It is also called as reaction enthalpy. In chemical reaction, we know that reactants react with one another to form products. The enthalpy change accompanying a reaction is called reaction enthalpy. The enthalpy change of a chemical reaction is represented by the symbol delta RH. Delta RH is equal to sum of enthalpies of products minus sum of enthalpies of the reactants. So that is delta RH is equal to sigma RH enthalpies of products minus sigma enthalpies of reactants. So please consider the example for the reaction CH4 gaseous form plus 2O2 in the gaseous forms combined to form CO2, which is also in a gaseous form, plus 2H2O which is in liquid form. So therefore here the enthalpy change can be represented as the reaction enthalpy delta RH is equal to sigma I of AI into H products minus sigma I of BI H reactants. Therefore, that can be represented as HM, that is molar enthalpies of carbon dioxide. This here in this reaction, the gas is CO2, CO2 gaseous plus 2HM of H2O, that is molar enthalpies minus HM of CH4 plus 2HM of O2. So these are this after negative sign is reactants, and the first term in this equation is of products given on the right hand side, and it is the react minus reactants where HM is the molar enthalpy. In this equation, AI and BI are stoichiometric coefficients, that is coefficients of the products and reactants respectively in the balanced chemical equation. In the example, it is a balanced chemical equation. Standard enthalpies of reaction. Enthalpy of a reaction depends on the condition under which reaction is carried out. It is therefore necessary that we must specify some standard conditions. The standard enthalpy of a reaction is the enthalpy change for a reaction when all the participating substances are in their standard states. So what is a standard enthalpy reaction? The standard enthalpy of reaction is the change in enthalpy for a reaction when all the participating substances are in their standard states. The standard state of a substance at a specified temperature is its pure form at 1 bar atmosphere. For example, the standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 1 bar. The standard state of solid iron at 500 Kelvin is pure iron at 1 bar. Usually data are taken at 298 Kelvin. Standard conditions are denoted by adding subscript, not subscript, superscript, encircled negative sign. That is encircled dash, which is shown here. The standard conditions are represented by adding a superscript encircled dash. This is encircled dash to the symbol delta H. That is delta example delta H superscript encircled dash. Some books don't write, have not shown any this dash sign. Simply they will write encircle, a circle at the superscript. Both may be correct. Application. Enthalpy change is very useful quantity. Knowledge of enthalpy change is required for planning the heating or cooling of required cooling planning and heating or cooling required to maintain an industrial chemical reaction at constant temperature. It is also required to calculate temperature dependence of equilibrium constant. Enthalpy changes during phase transformations. Phase, phase transformations are fusion, vaporization, and sublimation. Phase transformations involve energy changes. For example, ice requires heat for melting. Normally, this melting takes place at constant pressure, that is atmospheric pressure, and during the phase change, temperature remains constant at 273 Kelvin. Fusion, the enthalpy change that accompanies melting of 1 mole of a solid substance in standard state is called standard enthalpy of fusion or molar enthalpy of fusion. It is represented by the symbol delta FUS into H encircled dash, which is shown on the screen. This is the symbol for enthalpy change of fusion. So here the solid is transformed, melts and becomes liquid, and the enthalpy is delta fuse into H dash. Vaporization. Amount of heat required to vaporize 1 mole of a liquid at constant temperature and at constant under standard pressure 1 bar is called standard enthalpy of vaporization or molar enthalpy of vaporization. So, molar enthalpy of vaporization, whose symbol is delta VAP H encircle dash, and in this for this liquid becomes gas, and the molar enthalpy or standard enthalpy is delta VAP into delta VAP H encircle dash. Sublimation. Standard enthalpy of sublimation is represented by the symbol delta sub H encircle dash is the change in enthalpy when 1 mole of solid substance sublimes at a constant temperature and under standard pressure 1 bar. So in this, for sublimation, solid directly becomes a gas without going into the state of liquid, and it is represented by delta sub H encircle dash. The magnitude of enthalpy change depends on the strength of intermolecular interactions in the substance undergoing the phase transformation. For example, strong hydrogen bonds between water molecules hold them tightly in liquid phase. For an organic liquid such as acetone, the intermolecular dipole interactions are significantly weaker. Thus, it requires less heat to vaporize 1 mole of acetone than does to vaporize 1 mole of water. table in the next slide gives the value of standard enthalpy changes of fusion and vaporization for some of the substances. Let us take an examples of fusion, vaporization and sublimation. Example for fusion, H2O becomes solid becomes H2O liquid. So delta F H dash is 6 kilojoules per mole. Here delta first H encircled is enthalpy of fusion in standard state. If water freezes, then the process is reversed and equal amount of heat is given off to the surrounding. Melting of a solid is endothermic and so all enthalpies of fusion are positive. Please note all the enthalpies of fusion are positive. Vaporization. Water requires heat for evaporation. At constant temperature of its boiling point Tb and at constant pressure, H2O liquid becomes H2O gas. Therefore, delta VAP H encircled dash is plus 40.79 kilojoules per mole. So, delta VAP H dash is the standard enthalpy of vaporization. Last and final example is sublimation. Sublimation is direct conversion of solid into vapor. So, solid carbon dioxide or dry ice sublimes at 195 Kelvin with delta sub equal to 25.2 kilojoules per mole. Naphthalene sublimes slowly and for this the delta sub H dash is 73.0 kilojoules per mole. The standard enthalpy changes of fusion and vaporization are shown in the table number 1 and the respective melting point Tf and the boiling point Tb of the elements and compounds are also shown. Take for example, in the case of N2 that is nitrogen, the melting point of nitrogen is 63.15 Kelvin and its standard enthalpy fusion enthalpy change is 0.72 which is whose unit is kilojoules per mole and the boiling point of nitrogen is 77.35 Kelvin and its standard enthalpy change H way of vaporization is 5.59. Similarly, for other substances like NH3, HCl, CO, CH3COO, CH3, CCl4, H2O, NaCl and C6H6 are also shown in this table. Please pause this table and note down its values and study that how the melting point, delta fusion H and delta vaporization H boiling points vary from substance to substance. We will solve some numerical example. Question number 2. A swimmer coming out from a pool is covered with a film of water weighing about 18 grams. How much heat must be supplied to evaporate this water at 298 Kelvin? Calculate the internal energy of vaporization at 298 Kelvin given that delta VAP H naught for water at 298 Kelvin equals 44.01 kilojoules per mole. Please read the question once again. I will proceed with this solution. The process of evaporation is water H2O 1 mole of water vaporizes to become 1 mole of H2O gas, that is steam, and this is given in this equation. So number of moles in 18 grams of water in liquid is 18 grams divided by 18 grams per mole. So heat supplied to evaporate 18 grams of water at 298 degrees Kelvin is N into delta VAP H naught. That is equal to 1 mole into 44.01 kilojoules. Delta VAP value of delta VAP H naught is given in the question itself. That becomes, converting into kilojoules, 44.01 kilojoules. And here we have assumed that steam behaves as an ideal gas. So change in internal energy and delta VAP U is equal to, for vaporization, equals delta VAP H naught minus P into delta V. That is using the formula U is equal to H minus PV. So that is equal to, value of PV is a delta NGRT. So we have used, substitute P delta V as delta NG into RT using ideal gas equation. So therefore delta VAP H to the power of V vaporization minus delta NGRT equals 44.01 kilojoules minus, we have substituted the value of NGRT, that is 1 into the moles is the, here it is liquid and the value is it minus 1 into 8.31 kilojoules per mole into, that is 298 Kelvin, 10 to the power of minus 3 kilojoules per joule. So that is equal to delta VAP UV is equal to 44.01 kilojoules minus 2.48, and its value simplifying is 41.53 kilojoules. Next question. Assuming water vapor to be a perfect gas, calculate the internal energy change when 1 mole of water at 100 degrees centigrade and 1 bar pressure is converted into ice at 0 degrees Celsius. Given the enthalpy of fusion of ice is 6 kilojoules per mole, heat capacity of water is 4.2 joules per gram. The change takes place as follows. 1 mole of water liquid at 100 degrees centigrade becomes 1 mole at 0 degrees centigrade liquid. That, let it be, the change of enthalpy be delta H1. 1 mole of water at 0 degrees centigrade in liquid form becomes 1 mole of H2O solid at 0 degrees centigrade. That is, the water at 0 degrees centigrade is becoming ice. Let it be delta H2. Total enthalpy change will be delta H is equal to delta H1 plus delta H2. That is equal to delta H1 is equal to mass into specific heat into change in temperature. So therefore delta H1 is equal to minus 18 into 4.2 into change in temperature is 100 degrees Celsius. That is equal to minus 7560 joules per mole, and converting into kilojoules we get minus 7.56 kilojoules per mole, that is 7.60 divided by 1000. So delta H2 is given as 6 kilojoules per mole. Therefore delta H will be equal to delta H1 plus delta H2. Adding these two quantities we get delta H is equal to minus 13.56 kilojoules per mole. There is negligible change in volume during change from liquid to solid state. So we can assume it as a constant value. So therefore P delta V is equal to delta NGRT, that is equal to 0. There, because constant value. Therefore delta H is equal to delta U is equal to minus 13.56 kilojoules per mole. Standard enthalpy of formation. The standard enthalpy change for formation of 1 mole of a compound from its elements in their most stable states of aggregation, also known as reference states, is called standard molar enthalpy of formation. So, the standard enthalpy of formation of 1 mole of compound from its elements in their reference state is called standard molar enthalpy of formation. Its symbol is delta subscript F H naught. So delta subscript F indicates it is formation. Please don't get confused with subscript FUSS, that was for fusion. Delta subscript F is for formation. Delta F H naught, where subscript F indicates that 1 mole of compound in question has been formed in its standard state from its elements in their most stable states of aggregation. The reference state of an element is its most stable state of aggregation at 25 degrees centigrade and 1 bar of pressure. For example, reference state of dihydrogen is H2 gas, and those of dioxygen, carbon and sulfur are O2 gas, graphite and sulfur in rhombic state respectively. It is important to understand that a standard molar enthalpy of formation delta F H naught is just a special case of delta R H naught. So you can see examples 1, 2, 3 in the next slide. By convention, standard enthalpy of formation delta F H naught of an element in reference state, that is in most stable state of aggregation, is taken as 0. General equation for enthalpy change. So the general equation can be written as delta R H naught is equal to sigma, that is summation I AI delta F H naught of products minus sigma I of Bi delta F H naught reactants. So it is the standard enthalpy of formation of products minus standard enthalpy of the reactions. Here A and B represent the coefficients of the products and reactants in the balanced equation. So in the balanced equation, AI is the coefficient of product, which is on the right hand side of the equation, and reactants, which is normally in the left hand side of the chemical reaction. Examples. Consider the reaction H2 gas plus half O2 gas combine to form H2O in liquid state. So delta F H naught dash is minus 285.8 kilojoules per mole. This is given from the standard table, which you can copy from the NCERT textbook. Second equation is carbon, which standard state is graphite and it is in solid state, plus 2H2 in gaseous state combined to form CH4 in gaseous state, and its delta F H naught equals minus 74.81 kilojoules per mole. Third example is 2C, that is 2 molecules of graphite, 2C graphite in solid state combined with 3H2 gas plus half O2, combine all these three elements combined to form C2H5OH, which is in liquid state. So product is in liquid state, whereas reactants are, one is in solid and the two are in gaseous state, and its delta F H naught is minus 277.7 kilojoules per mole. Here 1 mole of compound is formed from its constituent elements, that is 1 mole each of water. Here water, here it is methane, CH4 is methane, and here C2H5OH is ethanol is formed from its constituent elements. Now we'll consider some special case which are exceptions to these delta F H naught. The enthalpy change for exothermic reaction. So consider the reaction CaO in solid state plus CO2 in gaseous state combine to form CaCO3 which is in solid state. So here delta F H naught is minus 178.3 kilojoules per mole. This is not an enthalpy of formation because calcium carbonate, which is a compound in the right hand side CaCO3, is not an enthalpy of formation of calcium carbonate, since calcium carbonate has been formed from other compounds and not from its constituent elements. Second example is H2 in gas plus Br in liquid state. H2 in gaseous plus Br2 in liquid state combine to form 2HBr, which is in gaseous state, and its reactants enthalpy delta RH minus is minus 178.3 kilojoules per mole. This is also here 2 moles. Here you see 2 moles are there on the right hand side instead of 1 mole of the product is formed from DRH minus of 2DF delta F H naught. So here it is 2 delta F H naught. Therefore, by dividing all the coefficient in balanced equation by 2, expression for enthalpy formation can be HBr can be written as we can rewrite this equation number 5. So it becomes, we have to divide it by 2. Half H2 gaseous plus half Br2 liquid equals HBr gaseous. So delta F H naught is equal to minus divided by 2. Its delta F H naught is minus 36.4 kilojoules per mole. Delta question. Let us consider one question. Delta RH naught to find the delta RH naught to decompose calcium carbonate to lime and carbon dioxide, that is CaCO3 in solid state decomposes to form CaO in solid state plus CO2 in gaseous state. We have to find the delta R of H naught, delta R H naught. Let us solve it. So delta R H naught is equal to delta F H naught equals sigma I of AI delta F H naught of products minus sigma I of BI delta F H naught of reactants. Here reactants are products sigma I CaOS delta F CO2 H minus, this is products are on the right hand side, minus sigma I of delta F CaCO3, that is in solid state. Therefore, from the tables we can find the values of delta F of H naught of CaO, that is equal to 1 into 63.5 into 1 plus 1 into 1 mole of 393.5 kilojoules per mole minus of this 1206 kilojoules per mole. Therefore, that its value is 178.3 kilojoules per mole. Thus, the decomposition of CaO3 solid is an endothermic process and we have to heat it for getting the desired products. Thermochemical equations. A balanced chemical equation together with the value of its delta RH is called thermochemical equation. That is, the equation must have the balanced chemical equation plus the value of delta RH. That is a thermochemical equation. The physical state along with allotropic state of the substance is also specified in an equation. Example, C2H5OH in liquid state plus 3O2 in gaseous state combine to form 2CO2 in gaseous state plus 3H2O in liquid state. All these combine to form thermochemical equation. And its delta RH value also should be mentioned. That is delta RH to the power of minus encircled minus equals minus 1367 kilojoules per mole. This equation describes the combustion of liquid ethanol at constant temperature and pressure, and the negative sign of delta RH to the power of minus of enthalpy change indicates that this is an exothermic reaction. Conventions of thermochemical equations. The coefficient in a balanced thermochemical equations refer to the number of moles. So here the coefficient is 1, 3, 2 represent the number of moles. Number of moles, not molecules, of reactants and the products involved in the reaction. Point number 2 is the numerical value of delta RH naught refers to the number of moles of substance specified by an equation. Standard enthalpy change will have its unit as kilojoules per mole. The unit for delta RH naught is kilojoules per mole, which means per mole reaction. Lavoisier and Laplace law. When chemical equation is reversed, the value of delta RH naught is reversed in sign. For example, nitrogen gas plus H2 gas combine to form 2NH3 in gas, and its delta RH naught value is minus 91.8 kilojoules per mole. And when the reaction is reversed, we can write the equation as chemical equation as 2 of NH3 gaseous splits to form N2 gas plus 3H2 gas, and its delta RH naught value is plus 91.8 kilojoules per mole. Please see the change in sign when the chemical equation is reversed. Please note it very carefully. Examples. Let us consider some examples. Calculation of heat. So consider the equation Fe2O3 plus 3H2 gas combine to form 2FeS plus 3H2O in solid and liquid state respectively. Given delta F H naught 2H2O in liquid form equals minus 285.83 kilojoules per mole, and delta H naught of FeO3 in solid state equals minus 824.2 kilojoules per mole, and its delta F H naught value of FeS is 0, and The values are given. Delta F H naught H2 gas equals 0 as per convention. Therefore, solution is delta F H1 naught is equal to 3 into H2. H2 is here minus 285 in liquid state. H2 is minus 285.83 kilojoules per mole minus 1 into 824.2 kilojoules per mole. That is equal to minus 875.5 into 824.2 kilojoules per mole. Simplifying, we get minus 33.3 kilojoules per mole. Therefore, for a different balance equation, we can write another equation dividing it by 2. Half of Fe2O3 in solid state plus 3 by 2 H2 in gaseous state combine to form FeS plus 3 by 2 H2O. That is, we have written this equation 1 in another form. So, we can rewrite the delta F H2 naught values. That is equal to 3 by 2 minus 285.83 kilojoules per mole minus half of minus 824.2 into 824 kilojoules per mole. That is equal to minus 16.6 kilojoules per mole. It shows that enthalpy is extensive quantity because of negative sign. Hess law of constant heat summation. We know that enthalpy is a state function. Therefore, the change in enthalpy is independent of the path between initial state and the final state. In other words, enthalpy change for a reaction is the same whether it occurs in one step or in a series of steps. So this can be stated as Hess law, which states that if a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. That is, in general, if the enthalpy of an overall reaction A to B along one route is delta RH and delta RH1, delta RH2, delta RH3, etc., representing enthalpies of reactions leading to the same product B along another route, then we can say that delta RH is equal to delta RH1 plus delta RH2 plus delta RH3. This is indicated in the figure above. Consider the enthalpy of change for the reaction as an example. So, the reaction, carbon graphite in solid state form combines with oxygen in gaseous state, combine to form CO gas, and we are required to find delta RH. Consider the following reactions. So we can write it as carbon, graphite and solid state combines with oxygen in gaseous state to form CO2 in gaseous, and whose delta RH naught is minus 393.5 kilojoules per mole. Let it be equation 1. Carbon monoxide plus half O2 in gaseous state combine to form CO2 gaseous, and whose delta RH value is minus 283.0 kilojoules per mole. Let it be equation 2. Combine the above two equations 1 and 2 to obtain the desired equation. To get 1 mole of carbon monoxide gas on the right hand side of equation 1, here this equation, we reverse the equation 2 to in this heat is absorbed instead of heat is being released. So the change of sign will be, there will be change of sign in delta RH value. So the same thing can be written as CO2 gas splits to form CO gas plus O2 oxygen, and delta RH naught is 283.0 kilojoules per mole. Adding 1 and 3, we get the desired equation. So carbon graphite in solid state plus half of O2 gas combined to form CO gas, for which delta RH is equal to minus 293.5 plus 283.0, that is equal to 110.5 kilojoules per mole. Enthalpies of different types of reaction. Enthalpies of combustion. It is the enthalpy change that is heat evolved accompanying the complete combustion of 1 mole of substance in oxygen at a given temperature and 1 bar. Example, C2H5OH in liquid state plus 3O2 oxygen gas combined to form 2CO2 gas plus 3H2O liquid, that is equal to delta CH naught. That is enthalpy of combustion is equal to minus 1365.6 kilojoules per mole. Enthalpy of atomization, represented by symbol delta subscript A H naught. It is the change in enthalpy when 1 mole of substance is converted into its atoms in gaseous state at a given temperature and 1 bar pressure. Example, carbon graphite reacts to form carbon gas and atomizes delta A H naught equals 716.68 kilojoules per mole. In the case of elements in solid state, it is equal to the enthalpy of sublimation. CH4 gas splits to form carbon gas plus 4H gas. So delta A atomization H naught equals 1660 kilojoules per mole. That Hg in liquid state splits to form Hg gas, sublimes to form. So delta A H naught 61.32 kilojoules per mole. So for elements in liquid state, it is equal to enthalpy of vaporization. So liquid is vaporizes to become gas. Bond enthalpy. Its symbol of bond enthalpy is delta bond H encircled dash. H to the power of encircled dash. So bond dissociation, it can be written as bond dissociation enthalpy and mean bond enthalpy. So bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bonds of gaseous covalent compound is broken. So covalent bonds are broken here and to form the products in the gaseous phase. Mean bond enthalpy is the average value of bond dissociation energy for a given type of bond. So it can be written as delta RH naught is equal to bond enthalpy of reactants minus bond enthalpy of products. Please note down these important points. The next enthalpy for different types of reaction is lattice enthalpy. Lattice enthalpy of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in gaseous state. Since it is impossible to determine the lattice enthalpies directly by experiment, we use an indirect method where we construct an enthalpy diagram called a Born-Haber cycle, which is shown in the figure on the right hand side of your screen. Let us calculate the lattice enthalpy of Na plus Cl minus solid by following steps given below. The reaction is shown on your screen. The first one is Na solid to Na gas. This is sublimation of sodium metal delta sub H naught, that is equal to 108.4 kilojoules per mole. The next one is sodium gas to sodium plus gas plus an electron, that is it gains one electron, that is the ionization of sodium atoms. Ionization enthalpy, whose value is delta I H naught equals 496 kilojoules per mole. The third one is half Cl2 gas to Cl gas. The dissociation of chlorine. The reaction enthalpy is half the bond dissociation enthalpy, that is half of delta bond H naught equals 121 kilojoules per mole. The fourth one is chlorine gas gains one electron, that is in gaseous state, to form chlorine minus negative in gaseous states. It is called electron gain by the chlorine atom. The electron gain enthalpy delta Eg H naught is equal to minus 348.6 kilojoule per mole. So we have learnt about ionization enthalpy and electron gain enthalpy in our unit 3. The next enthalpy is enthalpy of solution, whose symbol is delta sol solution H naught minus. Enthalpy of solution of a substance is the enthalpy change when 1 mole of it dissolves in a specified amount of solvent. The enthalpy of solution at infinite dilution is the enthalpy change observed on dissolving the substance in an infinite amount of solvent, when the interaction between the ions or solute molecules are negligible. So it is delta sol is represented by delta lattice plus delta hydration H minus, where delta hydration is the enthalpy of hydration of ions. Enthalpy, the next one is enthalpy of dilution. It is known that the enthalpy of solution is the enthalpy of change associated with the addition of a specified amount of solute to the specified amount of solvent at a constant temperature and pressure. With this, we have come to the end of the enthalpy types. Now we will revise some important points which we have learnt in this section, which will help you in solving the numerical problems and objective type questions. Internal energy is sum of all forms of energy, kinetic energy plus potential energy. Therefore, change in internal energy equals final internal energy minus initial internal energy. Internal energy for ideal gas is zero because particles do not interact and potential energy is zero. And further, in isothermal process, temperature is constant. Therefore, kinetic energy is also equal to zero. Therefore, internal energy for ideal gas is zero. The next relation is enthalpy. Enthalpy H is equal to U plus PV, where U is the internal energy and PV is the work done. The change in enthalpy represented by delta H is equal to delta U plus delta PV, and that can be written as delta H equals delta U. We know from our ideal gas equations that PV is equal to nRT. Therefore, delta H is equal to delta U plus delta nRT because PV is equal to nRT from our gas laws. The next point is most of the reactions are carried out at constant pressure and constant temperature. Therefore, delta H is equal to delta U plus delta N subscript G into RT, where R is the gas constant and Ng is the number of gas molecules. And the number of gas molecules is equal to number of molecules for protons and Nr is number of molecules for reactants, number of gas molecules for products and reactants respectively for gases only. Please underline it is for gases only. Please note that delta H is greater than 0. In that case, the process is endo, endothermic and it absorbs heat. Delta H is less than 0 and it releases heat and the process is exothermic. Enthalpy is 0 in a cyclic process. Enthalpy is an extensive property which depends on the amount of the substance. First law of thermodynamics states that delta U is equal to delta Q plus delta W, where delta U is the internal energy that is equal to heat content, delta Q heat content plus work done, delta W is work done. Therefore, delta H is equal to QP, that is enthalpy is nothing but equals amount of heat. Delta H is equal to heat content at constant pressure. Therefore, delta H is equal to delta QP. Internal energy delta U is equal to heat content at constant volume. That is delta U is equal to delta QV and delta H is equal to delta QP. Please note down all these important points as it will help you in solving numerical problems. First question, which of the following expression is correct to calculate enthalpy of a reaction? Four options are given. You have to remember the relationship, okay, and mark the correct answer. The correct answer is part C, that is delta H reaction is equal to delta bond enthalpy minus sigma bond enthalpy of products. I will read once again the correct answer. Delta H reaction is equal to sigma bond enthalpy of reactants minus sigma bond enthalpy of products. Next question. If enthalpy of an overall reaction X tending to Y, X becoming Y along one route is delta RH and delta RH1, delta RH2 and delta RH3 represent the enthalpies of reactants leading to same product Y, then delta RH is. Four options are given. You have to mark the correct answer. Please read the four options and mark the correct answer because you have to remember it. And this is you have to recall H's law and mark that option A is the correct answer. Next question. Hess law is applicable for determination of heat of option A, transition, formation, reaction, and option D is all of these. So you have to remember that Hess law is applicable for both transition, formation, and all reaction. That is all these. So option D is the correct answer. Mark it. Next, the statement, the change of enthalpy of a reaction is same whether the reaction takes place in one or several steps is. Four options are given. Which law you have to identify, whether it is a Lee-Jacquiers law, Van 't Hoff's law, first law of thermodynamics, or Hess law. So you have to remember and mark that it is pertaining to Hess law. So option D is the correct option. Next question. For reactions of 1 mole of zinc dust with 1 mole of sulfuric acid in a bomb calorimeter, delta U and W correspond to. So you have to mark the correct answers. Four options are given. So explanation is given in the inside box. Reaction in bomb calorimeter is at constant volume, so W equal to 0. So delta U is equal to Q, and the reaction of Zn plus H2SO4 combined to form ZnSO4 plus H2. This reaction is exothermic. Therefore, some heat will be evolved, which results in lowering of internal energy. Hence, delta U will be less than 0. Hence, this less than 0 and W equal to 0. This option is available as option A. Please mark it. Next question is 4 grams of graphite is burnt in a bomb calorimeter of heat capacity 30 kilojoules per Kelvin in excess of 1 atmospheric pressure. The temperature rises from 300 to 304 Kelvin. What is the enthalpy of combustion of graphite in kilojoules per mole? So you have to make some calculations which are shown in the inside box. So we should remember that in case of bomb calorimeter, Q is equal to minus CV into delta T into capital M by small m. These all the descriptions of all the parameters in this equation are given in this video itself. So mark it. So the value of CV is given as minus 30 into delta T is 4 degrees, that is 300 to 304 into capital M is 12. You have to remember that, divided by small m is 4 grams it is given. So therefore, simplifying, we get the answer as delta H is equal to minus 360 kilojoules per mole. So this is given as option C. Please mark it. In reactions, S plus 3 by 2 O2 combine to form SO3 plus 2 in 2x kilocalories and SO2 plus half O2 combine to form SO3 plus y kilocalories. The of heat formation of SO2 is, so you have to identify for these two equations by solving it. So I will proceed with the explanations. S plus 3 by 2 oxygen, S plus 3 by 2 O2 combined to form SO3 plus 2x kilocalories. It is the equation 1. And the second equation given is SO2 plus half O2 combines to form SO3 plus y kilocalories. So solving this equation 1 and 2, we get S plus O2 combined to give SO2 plus 2x minus y kilocalories. So therefore heat formation of SO2 is 2x minus y kilocalories. Please mark it. This option D. Next question is the heat of combustion of carbon, sulfur and CS2 are minus 393.3 kilojoules, minus 293.7 kilojoules and minus 1108 kilojoules. What will be the heat of formation of CS2? Four options are given and I will go ahead with calculations. So the given equation is C plus 2S combined to form CS2. Therefore, this can be written as delta H is equal to sigma delta H of product minus sigma delta H of R. So the values are given. So delta H of P is 1108.76 minus 393.3 plus 2 into 293.7, that is equal to 1108.76 plus 393.3 plus 587.4. Simplifying, we get the answer as minus 128.06 kilojoules. So this is given as option A. Please mark it. The next question. 1 mole of an ideal gas undergoes change from 3 atm 5 liter 80 Kelvin to 6 atm 7 liters 200 Kelvin with a change in internal energy of 5 liters dash atm. Find the change in enthalpy. Four options are given. Let us go ahead with solutions. So given items are written and we have to find delta H is equal to what? So it is given by the relation delta H is equal to delta U plus delta PV. Therefore, delta H is equal to delta U plus delta into PF VF minus PI VI. Therefore, delta H is equal to 50. Delta U is equal to 50 plus 6 into 7 minus 3 into 5. Substituting the value of PF, VF, PI and VI, we get the answer as 77 L-M. This answer is given as option A. Please mark it. Next question is find delta H is greater than or equal to delta U for the following reactions. N2 gaseous plus 3H2 gaseous is reversible process 2NH3 gaseous. Reaction 2 is H2 gas plus Br2 gas form combined to form 2HBr gaseous. And the third equation is MgCO3 in solid splits to form MgO solid plus CO2 gas. So four options are given. You have to identify the correct answer by solving it. So for the first reaction, Np minus Nr, that is Ng is equal to Np minus Nr, that is equal to Np is 2 and Nr is 3 plus 1 4, that is equal to 2 minus 4 equal to minus 2. Therefore, delta H is equal to delta U minus 2 RT. That means delta H is less than delta U. The next reaction, for the second reaction, delta Ng is equal to Np minus Nr, and here Np is 2, coefficient is 2, and for the right hand side equation 1 plus 1 2. Therefore 2 minus 2 equal to 0. Hence Np minus Nr equal to 0 and delta H is equal to delta U. And for the third reaction, left hand side Np is 1, that is the coefficient of gaseous state is 1 minus, there is no gas item on the left hand side. So Nr is 0. Therefore 1 minus 0 is 1. Therefore substituting in equation delta H is equal to delta U plus RT, we get that delta H is greater than delta U. So these options are available as option A. Please mark it. Next question. Find the value of delta H minus delta E. Delta E and delta U both are same. Some books write delta E and some places we write delta U for the reaction. So the given equation is written on the screen, that is 2C6H6 in liquid form with 15 oxygen in gaseous form combined to form 12 moles of carbon dioxide in gas and 6 moles of H2O in liquid form at 25 degrees centigrade. We have to find the relationship between delta H minus delta I. Four options are given. So we know that delta H is equal to delta U plus delta HgRT. So we have to remember the value of R is equal to 8.314 joules per mole Kelvin. T is equal to given as 25 degrees centigrade. That Converting into Kelvin, it is 298 Kelvin. We have to find delta H minus delta U is equal to what? Therefore, Ng is equal to Np minus Nr. So, here in this equation, right side gas is 12. Therefore, Np is 12. On the left hand side, the gaseous part has got coefficient 15. So, minus 15. So, we have to consider only the coefficient of elements in gaseous state. So therefore it is Np minus Nr is 12 minus 15, that is equal to minus 3. Therefore the value of delta H minus delta U is equal to delta NgRT, and delta N we have to find Ng we have found as minus 3 in the previous step into 8.314 into 298. Simplifying, we get the answer as minus 7432.7 joules. So for converting into kilojoules, we have to divide it by 1000. Therefore, 7 minus 7432.7 divided by 1000, that is equal to approximately equal to 7.4 kilojoules. That is given as option A. Please mark it. Next question. Find the difference between heat content at constant pressure and heat content at constant volume for reaction C3H8 gaseous plus 5O2 gaseous combined to form 3CO2 gas plus 4H2O liquid at temperature T. So we have to find the and mark the correct answer. Four options are given. Let us go with solutions. C3H8, that equation is written, same equation represent, and we have to find QP minus QV equals what? Therefore, delta H minus delta U is equal to, that is the difference between heat content at constant pressure and heat content at constant volume is delta H minus delta U, that is equal to delta NgRT. So we have to calculate delta Ng. Delta Ng is equal to Np. Np on the product right hand side of gaseous is 3, and on the left hand side we have gas, both are gases, that is 5 moles of oxygen and 1 mole of C3H8, that equals 5 plus 1 is 6, 3 minus 1 6 is minus 3. Therefore, delta NgRT is minus 3 RT. This answer is available as option A. Please mark it. With this, we come to the end of lecture number 2 of thermodynamics. In the next lecture, we will discuss about spontaneity, Gibbs energy change and equilibrium. Till then, goodbye.